Thank you. And thank you very much for inviting me. It's my first time here and I'm really enjoying it. So in my talk, we will move into yet another kind of music than we've been talking about yesterday and this morning. But I think the underlying question that I'm interested in actually relates to a lot of what has been said yesterday and today. So I want to talk about computational music analysis. And like the overall frame are two questions that I would like to look at. So what do we really know about music when we think we know? And what do we learn about music when we know that we don't really know? And what is the task of computation here? And these two questions. And I've seen this also very fruitful throughout Gopala's thesis, where he reports that, in the art music, we have a tradition of 2,000 years, and we have lots of treaties. So it's a very well documented musical culture. And then we have today the musicians that are taught in a, I'm not sure how I pronounce that correctly, guru, shishya, parampara system. So where it's from teacher, student, teacher, student. And so highly, highly trained, you somehow become an expert by doing this. But what we often see is that the expert is fantastic in doing it, but not very fantastic in explicating how he or she is doing it, which for us as computer scientists often make our work hard. And actually, I would say, I'm trained in classical music. I would say that's the same way in the European system. So you start learning to play an instrument, not by rules or by looking into books, but what your teachers tell you, and you become an expert over years. And then you try to extrapolate why is it that at some point you're slowing down or speeding up or do whatever, and you're not really good at that. So we have this concept of being a musical expert. Specifically, if you are a musicologist and you do music analysis, you really demand that you have to be an expert in the music. And sometimes, if you bring in the computation guy, and I'm allowed to say that because I'm also a musicologist, you're going like, well, you don't really understand this music, so how you dare? And I think looking at the other person as the non-expert. Now, what I think is that I have learned that in certain situations it's very good to be not the expert and to have to ask the seemingly stupid questions for finding out interesting things. And I think computation is just a fantastic tool of having to ask stupid questions, even about the music that you thought you were the expert on. Okay. So that brings me to the question, what the heck is an expert then? It's not that clear at all, right? Perhaps to say a little bit about myself. So what musical expert am I considered to be? I studied musicology and mathematics in Berlin. And musicology meant that I did have courses in ethnomusicology, but German musicology is mostly all about, of course, classical Western music. So that's what I thought I have learned. And then I did a PhD in the area of mathematical music theory. I then went to the US, did more on music, computation, and cognition. And then I moved to the Netherlands for a project where the task was to build a search engine for a large collection of Dutch folk songs. And so you see this, that's the Mertens Institute that hosts this collection. You see that in the middle. And when I moved there and we started the research project and I would, go to Izmir telling about this research, this made me into the folk song expert at Izmir. While sitting at the institute with all the musicologists, I was the technician. So, since then I have a little bit of an ironic relationship to this word expert. But perhaps that's most of the time we become experts because others see us, as being an expert. Now, what I would like to, the perspective that I would like to take in this talk is that I think when we are the musical expert, most of our knowledge is implicit. And computation gives us a chance to hopefully make some of that a bit explicit, test that on a data set and, by stumbling about all the things that don't work then, we hopefully also learn something back on what it is that we as humans know implicit, but perhaps have tested it in a way a little bit with our computational models, or perhaps have learned something else about how we learned it. And I will show you some examples from my own research group. Before I come to this, I still would like to talk a little bit more about this expert notion, because I found this very interesting quote from Shunryu Suzuki. He was, I think, a Zen master who transported Zen to the West. And he says, in the beginner's mind, there are many possibilities, and in the expert's mind, there are few. So he contrasts beginner's and expert's mind. Now, I'm not a Zen specialist with the full authority being able to explain what a beginner's mind is, but what I do understand is that it doesn't mean you have to be a fool, but that you have to be very open-minded, even with all the knowledge you have. Just look at the situation that is in front of you with an open mind and see what might work well or what might not work well. And the way I understand it, I realized, well, as a researcher, you have to have a beginner's mind, because otherwise you don't find any interesting question. And so for me, the computer is in a way a tool, even if I investigate the music that I think I am an expert about, I have to move into the beginner's mind mode again when I have to model it with computation. And then I figure out, oh, wait, I know less than I thought I would know. And so I think computational modeling, gives us a very fruitful area of combining the experts and the beginner's mind. Now, why am I enthusiastic about doing this? Where I think it's a very successful way, of a very promising way of doing research. And I was inspired actually about this by this book by Bernie Glassman called Instructions to the Cook, where I got this notion of the expert and the beginner. And this is not a cookbook. This is about his approach he built in the 1980s in New York, a bakery, with the goal to give homeless people a job so that they can, in a way, in the end, pay again a rent. Now he did this with a group of people, and they said, okay, so what job could we offer to them so that we can sell something and really pay them, without any state government money? And so they searched the market, and they came with, okay, we do a bakery. But none of them was a baker. So we're like, okay, we don't know how to do it. So they would fly an expert from San Francisco, and this expert baker gave them like the beginnings of how to do it in general. And then there are lots of chapters on how they describe how they experiment as total beginners on how to bake bread and to make cakes. And because they were total beginners, they in a way, ended up with a chocolate cake that was so special that even made it to the White House. So they really, really became very good in it. And when I read through this, I was very much reminded of how it is to finding computational models for music, because it's also a lot of trial and error. You think perhaps this data structure works, or perhaps that works. Often it doesn't work, and so you just stumble upon like a beginner. And what was a very interesting experience they had was that once they got rolling, they could pay a lot of people. They thought, well, we have to make this whole process more efficient. We don't do this efficiently, so let's fly in again the expert. So they would again fly in the expert, and the expert would show, how do you normally do this? And so they said, okay, so this is how we do it now. And then one of their main customer called and asked, what happened with your chocolate cake? And they what? Well, it's still okay, but the specialty is gone. So it turned okay. So, flying in the expert, all of a sudden made the very special cake into a normal cake, so they had to throw it out. Again, the expert knowledge, and just went with their way of doing. And just if this rings a bell with you, in computational modeling, where you sometimes have to throw out the expert knowledge, I really love that story. So, as I said, I would like to talk about the role of computation and how do we, in successful ways, combine the expert and the beginner, because I think that alludes a bit to what Tilman has said. In the history, of course, of musicology and computer science working together, this often went awfully wrong, right? So just one example from how Hewlett and Selfridge Field described the atmosphere in the 1960s when the bigger project started on computation and music. They say, well, musicologists anticipated really colossal returns. They really had very high hopes of what we could do. And then in the 1970s, if you look then into the literature, you realize that the people who do computational research really have to defend themselves. That they get accused like of the totally trivial questions. So what are you doing there? And so what they say, well, to defend themselves, there's little music theory available that I can use for implementing any of that, right? Or we seem to be without a sufficiently well-defined theory of music that would allow us. And running out of theory basically means running out of program code. So this means by bringing in the computation, we realized we are less of an expert of the music than we thought we are, because, if we would have made the knowledge more explicable, it would not be that hard to build those computational models, right? So that was a learning moment then. And I'm afraid we are not yet at the end. I come back to the same talk by Nicholas Cook in 2005, where he talked that computer science and musicology, in their relation, we stand at a moment of opportunity. So, which, sounds like you're standing at this door and just go out and full of expectation. But then the sentence ended, the trouble is we've been standing at this moment of opportunity for quite some time now. And I think there are lots of reasons why that moment is perhaps that long, but I think that how we are open and willing to combine experts and beginners' minds with each other is one ingredient of whether it works or does not work, when we try to work together. And I would like to show you an example where being not the expert did help to highlight some knowledge about Dutch folk songs. And so I start with this example of the folk song collections for which we got the task, please build us a search engine for this music, because we have now these 7,000 recordings that have been collected in the 1950s to the 1980s. And until that time, people who wanted to know about a certain folk song had to call the institute. They would call in and say, my father's funeral is next week, and he has this favorite song that we don't know about, so could you please, give us the notes and the text that we can learn it. And so they wanted to digitize all of that, make a search engine for the public, general public, that people could be able to find those songs themselves. So we got in the Witchcraft project the task, please build us such a search engine that is able to search through the collection by way of similarity. Now, these folk songs that have been recorded in the 1950s to the 1980s, they were all not notated. That's the nature of folk songs, right? It's orally transmitted. So there is a long history behind, from one generation to the next, that you sing and you listen and you sing. And of course, in this process, there's a lot of variation introduced into the folk songs. So that now that we have those 7,000 recordings, it means we have a lot of recordings that are very similar to each other, because probably in history, they go back to like one song that, in the different regions and through the different generations has produced a lot of variations. And we call that a tune family, or let's say the Mertens Institute, the specialists who would work with the collection, called that a tune family. And now the task was, okay, if you find a reasonable similarity measure for that collection, please find us automatically those tune families. That would be really cool. Now, we had at the Mertens Institute musicologists that had worked for years with those songs, and they had at the time already classified a number of 1,000 songs into tune families. And so we were there, the beginners, having to build the search engine. And so we asked them, okay, so then tell us, what is the similarity between the songs belonging to one tune family? And as computer scientists, we, expecting to get answers on features and weights and how to combine them. And the answer was like, well, that's obvious, you just listen to it. And, you know, as computer scientists, you think, what? You've been working with this for years and you don't even have a system? How dare you, right? And then they say, well, just do it yourself. Just listen to them. And that's what we did. So they gave us a number of tune families. And then you do this yourself, and then you realize, yes, of course, we are humans. We listen to the music, and in most of the examples, we have a very natural, intuitive, holistic idea. Yes, this is similar, or this is totally not similar. In some cases, we doubt, and then we start thinking, okay, so how would I reason? But most of the time, we just do it. And we don't know really how we do it. Now, our problem is that they insist that everyone can do it. And I looked over a lot of tune families, and some I understood, and there were also tune families that I said, well, I don't understand it at all. And we have only 4 years for the search engine. We will not get your knowledge on those 7,000 songs in 4 years, so you have to tell us more. And the beginning was that we would sit with them on the tune families, and for each tune family, okay, so what is here the simile? What is this? What is this? And they would drop words. They would drop words like global contour or, you know, the local rhythm. And we took this as a starting point to design actually an annotation study with them, because we felt like we need, you know, the most systematic way that we could get out of them to understand what the similarity might be based on. And that was actually a process of months, where we first started to give names to certain features they thought they were using. Then we all had to agree what it means. What do we understand, or what do they understand by a local contour, or by a tonal structure, or by a pattern? And then we would ask them to rate either a 0, that this feature would not contribute to the similarity between two songs, a 1, it in a way does contribute to the similarity, or 2, it very obviously contributes. And they felt able to give those 3 ratings, they were comfortable. And we then asked them to just give us, you know, a collection of very different tune families out of the whole data set. And so they would annotate 360 songs for us according to those ratings. And it turned out that what the most obvious feature was, even though in a way they all contributed, but the clearest was that the recurrence of patterns between songs that came out of that annotation study. And so we asked them then to annotate those patterns. I will show you them in a minute for those examples. So I will play you 2 folk song recordings from melodies that are supposed to be in the same tune family. Okay? And I have to say, those recordings were mainly older people, because they were doing the recordings because they were afraid that the culture is dying out if this generation has passed. So most of the recordings are a little bit older singers. So, okay, first song.
In England woont een koopman rijk en oud, die uit een dochter Margaretha was haar naam.
Okay, so that's the first song. And the second song.
In Engeland woont een koopman rijk en oud, die uit een dochter Margaretha was haar naam.
Okay, so that was again the first song. I hope now we hear the second.
Daar was een koopman rijk in Leiden, die had een dochtertje al om die zat.
All right, so I hope that's rather obvious similarity, that there is a relation. It's interesting that the text is rather different. So in a lot of those songs, you would not find those tune families by searching on the lyrics. So since the musicologist said it's, or what came out of the annotation study is that the repeated patterns are so important, we asked them then in a follow-up study to annotate those patterns. And here you see 2 examples of the blue and the red pattern. And as you see, it's not a literal repetition, so it's a little bit varied. And so we got a lot of those annotations. Now, if you look closer at what is annotated, you might think, well, wait a moment, why? I mean, why, for instance, why does this red pattern not start here already? Why, you know, so there are a lot of things, even if you look at it, that are debatable, and I will come later back on how we tested what's the value of those annotated patterns. But for now, let's say this was their answer. Now, meanwhile, in parallel, while we were doing the annotation study, we were still, as computer science, trying to bake a chocolate cake without really knowing how. But in the end, what we came up with, the most successful way of calculating the similarity between the songs that's also now implemented in the search engine, that's actually a sequence alignment based on note to notes. So that's implemented now. So you can go to the website, say, okay, here's all the metadata, and then you go to please find similar melodies, and you get a ranked list of all the others that are supposed to be similar. But again, the underlying algorithm is take one song and the other and do a sequence alignment. So there is nothing in here on patterns, right? I mean, every note is in a way respected equally, you could say. So we first like, well, okay, what does that mean? Is the conscious insight that the musical experts would give us very different to the computational solution that we found? We could more than 90% of the tune families reconstruct with that. So it's really a good method. But it didn't give us really an idea on what is the role of the patterns and any way of saying what is it that stays stable in oral transmission and what is it that changes. So since this idea of patterns was not only mentioned by the folk music, by the musicologists at our institute, but also if you look into the broader literature from ethnomusicology in other cultures where tune families have been investigated, a lot of musicologists say it's the patterns, or even that in a musical culture there are certain patterns that are recombined. It's like part of the musical knowledge of that culture. So we felt like, as an engineer, of course, we could say, well, task solved, right? Here's your search engine. But as musicologists, we stayed persistent with, well, we still want to understand what is this role of the patterns. My first idea is that, of course, as a human, and specifically Western musicologists, we always think about motifs and patterns, and perhaps we have just something made up that comes from classical music and transported that to folk songs. Anyway, so we came up with the idea that what we could relatively easily do as computer scientists, we could really take those annotated patterns and take them as a way to compress the songs. So if the musicologists say that like the most important information is contained in those annotated patterns, we could take them and basically throw away the rest and then try, what are the classification results we get then. Of course, we can't hardly beat something that's already over 90%, as in the note-to-note alignment on the full material, but if at least we, would get reasonable in that area by throwing away the rest, it could be an indication that still there is something in the notion of the patterns that the musicologists told us. And so this is a computational experiment that master students then did, and the idea was then you take those annotated patterns from the experts and you construct what we call a sparse melody and do the classification using only the sparse melody and not the entire melody. And the first idea was at least you should be better than if you take a random sparse melody, right? If you're better than that, at least it would show that perhaps there is really important information. Now, so basically what this master student, Peter Bott, did, he came up with this framework. How do we test that? We were not only interested in testing the annotated patterns from the musicologists, but also taking state-of-the-art pattern discovery algorithms, because it would be cool if you could do this, of course, automatically, and wouldn't have for, every data set, again, the musicologist to annotate that, which was hard enough to convince them to spend their time on that, right? So what we did was we would take the data set, we would run a couple of pattern discovery algorithms, construct then those sparse melodies. Of course, then you get as one aspect, the coverage. Of course, if you end up with a pattern discovery that basically covers all, that doesn't give you much, so you need to take into consideration what is the coverage. Then you do here a similarity calculation, do the classification, and then you get the accuracy. And then you try to compare that to the original result or to a random sparse melody. So as data sets, as I said, we took those annotated Dutch folk songs from this Dutch collection, but we also included an Irish folk tune data set just to test whether what we find is very specific for this Dutch tune, or whether this would also, apply to others. And, oops, sorry. Yes, so apart from, as I said, apart from the humanly annotated patterns, we would take 6 different algorithms, and we were also not sure whether the pattern discovery means that the patterns also reoccur within one song, or is it only patterns that recur between songs? So this was something else we tested, and we compared that to the human annotations. So the 6 different algorithms were algorithms by Olivier Latillot, David Meredith, Daryl Conklin, and Oyol Neto. Okay, now, as I said, most of those pattern finding algorithms are actually designed for finding patterns within one song. So we had to adapt them so that they could find patterns between songs. Basically, what we did was we would concatenate all the melodies that would belong to one tune family, do then the pattern search, and then throw away any pattern that's just random at the boundary, right? All right. We also tested different ways of how would you then construct the sparse melody construction. Actually, 3 ways. So you can see here the red, green, and red patterns. Those are repeated patterns. And so we have 3 different ways of constructing the sparse melody, either the on-set preserved reconstruction, where you just leave out anything else. Here you do a gapless reconstruction, so you snap everything together, and here you just take the very first pattern occurrence, just to play around with different ways of constructing those sparse melodies. And then, again, construct the melody with only notes from the patterns, which then results in a coverage where, well, he should stand the sparse melody, the number of notes in the sparse melody to the original, that gives you the coverage. Okay. And then we did a similarity calculation based on sequence alignment, and we compared note to note and melodic shape alignment. Okay, I think I don't have to explain to any of you how sequence alignment works, so I will skip that part. And then let's come to the classification. So we used one nearest neighbor classification with leave one out cross-validation. And then we get this accuracy. And then we were interested in plotting what is the accuracy and what's the coverage. So we tried different ways of compressing the songs, sparse melodies, of what patterns would we use, and then we would compare the annotated and the discovered patterns. The question was, what do we compare that to? So one idea was, because we can't get better than the 90%, so we can't say we want to beat the note-to-note alignment, but still, so what do you compare then those approaches to? One idea was just taking random notes out, but we figured out that's not really fair. You should at least try random patterns. That was the second step. So we would have like a random mask first created that we would run over all tune families, that you take patterns out of the songs. And another very naive baseline was just take the first, middle, or last end notes, right? That's like the most naive compression you could just think about. And then we would compare that actually to what happens if you take actually the pattern approach. Now, here are the results. There's no pattern yet here, just let me explain what you see. So here's the coverage, and there's the accuracy, and ideally we would like to be as far as possible here, that we get a high accuracy with low coverage. And here you see like what's the baseline or the original experiment where we take the note-to-note alignment. So we want to be as close as possible here. Now, if you take random notes, yeah, that's the worst case. If you take random patterns, it gets a bit better. But actually, the first N, the last N, or the middle N notes is already pretty good, which was, in a way, a bit disappointing. But what was interesting is now, if you take the annotated patterns, you end up, we see this on the next slide, we end up with the result here. So the annotated patterns you throw from the humans, you throw away 60% of the material, and here's the star. So the annotated pattern is still above that. However, unfortunately, this is not at all the case with any of the automatic pattern finding algorithms that exist. So here is the song pattern discovery, where we just searched for patterns that are repeated within one song, and obviously that was really not a good approach, because at least if you go to really searching the patterns between the songs, it gets a bit better. And Peter really exhaustively searched all parameters. So what you see is like trying all parameters per algorithm that exist. But still, as you see, we don't get there where the annotated patterns are. So basically what we learned, we can throw away 60% of the note material with the annotated patterns, and the classification accuracy drops from, I think, 0.93 to 0.88. That's interesting, because that in a way shows that, oh yes, there is something in the material of the annotated patterns, because you can throw away the rest and you have only a very low or a very small drop in the classification accuracy. It was kind of nice that this intuition from the musicologist was not completely wrong. So there is something in the patterns. Unfortunately, none of the current pattern discovery output gets anywhere close there, but we made the observation that if you highlight, here you see one tune family and the different melodies, and we highlighted same patterns with the same color. And obviously you see there's a certain order of how the pattern occur in the piece. It's not random, and none of those pattern discovery algorithms, they work very much bottom-up, so very much from local information. None of them takes anything like position or so into account. And this is what we are now working on. How can we also take the position into account and hopefully get better results with the automatic pattern discovery methods. And just a short note, in the Irish folk song data set, the picture looks very similar. Okay? So it was not just for the Dutch folk song data set. Okay. So what have we learned? Well, the naive compression methods work pretty well as well, just taking the first N, last N, or middle N notes. But at least the annotated motives still work, or annotated patterns work still better. And now the interesting question is, can we, with the automatic pattern discovery, can we improve them so to better get into what is it that the humans find in those patterns? Okay. So yeah, in a way it was a relief that in the first case we thought, the musicologists just cannot reflect, but no, it wasn't quite that. If you be persistent, there is something in their musical knowledge that has to be respected. Okay. But again, I think we went there because we had this combination of the experts who said this is totally obvious, and us who say no, it's totally not obvious, and trying to bang on this with computational methods on how could we measure, what is obvious or perhaps not so obvious. Okay. And actually, perhaps the last comment is that in the end, also the musicologists were really, really happy with the search engine, because they also had, of course, many melodies where they themselves were uncertain. Should I put this more into this tune family, or should I put this into that tune family? And they would use the algorithm and that would make suggestions, and sometimes they would, change their mind. And that was very nice to see, because in the beginning we would try algorithms that really would not work at all. And they were like, oh God, what are you doing? This is total unreasonable results. And it was very nice that at the end of the project we had something that also help them. But as I said, it required a heavy dialogue and also trying to convince them that they have to spend time on making those annotations for us, because otherwise we are just lost without knowing anything about the collection. Okay, now my second example that I would like to talk about is more from the typical MIR area of genre classification, right? We all want to do this, but as we know, at least since Bob Sturm, lots of articles, but this is really not a problem that we have solved at all. Now, if you ask musicologists, well, what is a genre at all? Well, either they say, well, let's just fake something, or they come up, well, perhaps it has something to do with patterning, or it has something with the musical material to do, or with repetition. So it looks like musicologists do think it has something to do, again, with finding patterns. And I think if you study then a genre, it's pretty obvious that you shouldn't try to find those patterns by hand, and perhaps you should use a computer, right? And the example that I would like to talk about is ragtime. And you say, well, why ragtime? What's difficult about ragtime? Right? So let's listen to one, which you, I'm sure, all know. All right, so that's the one example you all know, right? Now, I have a second example that's not ragtime, which is this one. Right, so that's 19th century romantic music by Edvard Grieg. And then I have a third example, and I'd like to ask you to think about whether that sounds like 19th century romantic piano or like ragtime. All right, so who votes for 19th century romantic piano music? Okay, and who votes for ragtime? Yeah, yes. But it's both, you're right. So I did this also to, some Dutch journalists who were saying, what's ragtime at all? Everyone agrees this sounds like a ragtime, whether you have heard the word ragtime or not. But what's interesting, it was again the Edvard Grieg piece, but it was played as a ragtime at a ragtime festival. Right? But it is a very obvious example that you don't have to be a big expert to hear that. I mean, most people hear that. So then if that's so obvious with ragtime, why do we want to study ragtime then? Well, actually, I found out that there is still a very lively ragtime, international ragtime community active that hosts lots of websites and collections and compose new ragtimes. And they say, well, actually, a discussion on what constitutes ragtime could fill several web pages. So by knowing one example, we think it's totally obvious, but that's not the entire story. So there's lots of actually songs. So for me, ragtime was piano music, but in the origin, it's actually a lot of songs. So it's a non-trivial question, what is ragtime? And so still, even now, we have different ragtime societies all over the world, and festivals. And it's not really clear what we should say is a ragtime. So Irvin Berlin, he's a ragtime specialist, and he looked into lots of ragtimes, also at large collections. And he said, well, yeah, the question is what still counts as a ragtime and what doesn't count as a ragtime. And one of the difficulties is how when ragtime evolved, it was like a hybrid from both folk and rhythm cultures. And so one attempt was understanding ragtime was by Berlin and by other musicologists was studying the sources of the time. So what did the contemporaries think about? Where did ragtime come from? You know, what the people, the musicologists or the ragtime lovers write about this? Right, so this is just the example that it came also a lot from piano rolls, where this first was an oral tradition before it made it into notation. Now, then if you study those sources on what the contemporaries thought ragtime is about, then you find all kinds of different arguments, like it came from the coon songs, or it came from the cakewalk, from the slaves in Florida. I think one note even argued, no, it even came from the Native Americans, from the Seminoles in Florida. Other sources argue there's a lot of influence from the dances of South America and the Caribbean that all come together to make this style. And the most exotic argument was, didn't Johannes Brahms contemplate a ragtime project? Of course, at least this we now know today, this is fake news, right? Because this was just, because ragtime in the beginning was, considered like dirty music, so not really well-respected concert music. And so the fans tried to make up arguments, that even, have highly respected Brahms because he had lots of syncopations, that also he would contribute to ragtime, but that's probably not really the case. So if you study the sources, then there are lots of different opinions of what came together in building the style. And this is where Urban Berlin said, well, actually, okay, I studied now the historic sources, but this gets me only that far, and I think I should study the musical material itself. And the trouble with the musical material is that most musicologists have studied only those three main composers, or probably also us. This is the music that we know, those three composers. But Edward Berlin says, well, actually, I don't even think that they are very representative of the style. So he said, well, actually, you should really try, we should take a more broader look on ragtime. And this is where I think, computational corpus-based study totally comes in handy in helping with those questions. And I was lucky enough just by, searching through all those ragtime websites that I found that there exists the rag collection that consists of 11,000 MIDI files and has a compendium with metadata on 15,000 identified ragtime compositions. So you know then, what year is it from, who's the composer, a lot of data, what's the year the composition comes from. And I got this data set sent via CD from Australia to Utrecht. But it's now available, so whoever wants to work with it, please mail us. And so we said, well, that's really cool. Now they contain really rags from the beginning to the present time, which was then 2012. And we could ask some questions on, okay, what might be characteristic patterns in the ragtime. And of course, what's an obvious way to go is rhythmic patterns. I also would like to talk about metric accent profiles on how we use them. I think I don't have to explain to any one of you what's the metric structure, right? So this is like the music theory way of explaining that. If you have a 3/8 time signature, you have like a hierarchic model of accents. And then the question is, well, how does it come into the music, right? Is it played? Is it somewhere in the score, even if you don't know the notation? How does this accent patterns comes into the music? And this was actually main part of my PhD thesis, where I would work with a computational model that we called intermetric analysis that would automatically, based on note onsets, induce metric weight profiles that kind of tell you, what's the accent structure of the underlying piece. So here's just one example for the beginning of Mozart's Jupiter Symphony. So you see the time axis from left to right. The higher the blue line, the greater the corresponding weight of the note. And in the background, I have just for orientation given where the bar lines are, but the model itself does not know anything about the bar lines. And then if you just zoom into the structure, it's in 4/4, and that's exactly what we get with the highest metric weights on the beginning of the bar. Then we have a second weight layer and the half bar, and then the 2 and 4, and then here are the weaker eighth notes in between. Now, if you use this model and analyze ragtime, then the typical pattern that you get is that the left hand very nicely tells you that it's in 2/4, but the right hand often is totally complementary, so that the high metric weights are not located where they are supposed to be according to the bar line, but they are in between, and that has to do with a lot of syncopation that takes place in the right hand. So we started to look into syncopation patterns, and the pattern that I have annotated here is the so-called 1-to-1 pattern that has been argued by ragtime specialists that that's the most typical syncopation pattern. And they say, well, this most typical ragtime syncopation pattern occurs in different forms depending on where it occurs in the bar, right? So it could be at different places. And they say, well, basically we distinguish the untied version because it's not in the middle of the bar or across the bar, and the tied version that's either in the middle of the bar or over the bar line. And then they say what happened in ragtime is that in the early times you would see a lot of the untied syncopation, and when the style developed, you would see more of the tied syncopation, because one hypothesis could be that this is really a stronger syncopation than this one. And of course, the general audience at the beginning of the 20th century wasn't really used to syncopation patterns. So, just what I said in the beginning, mainly the untied and then later the tied syncopation. And then we said, well, that's a very nice hypothesis that we could test on this data set. And we were also interested in what actually happened after the ragtime era, right? So the ragtime era is supposed to go until approximately 1920, but even after 1920, there are ragtimes all the way, specifically in that collection. And the question is, so what happens then? The style has been established. Does this mean, the syncopation pattern remain the same, or perhaps they get even stronger because we are, meanwhile all used to syncopation, but we couldn't find any notion on that from the literature. So most literature really stops after 1920. So we thought, well, that's interesting. We could come up, with some new observations from this data set. We had different ideas on what might happen. Perhaps there is no change because the genre has been consolidated. Perhaps it even increased. Or some said, well, a lot of those syncopation patterns later got replaced by dotted rhythms and led to a reduced need for syncopation. So who knows, perhaps the syncopation did decrease. Anyway, we did this on this data set, and what we found out first in comparing the early versus late ragtime and the ragtime era, yes, indeed, the use of the untied syncopation significantly decreased while the use of the tied significantly increased. So that was like a, kind of backing up the musicological hypothesis. And then if you compare the ragtime era to the modern times, or what we call modern times after 1920 until today, you see there is a slight increase, still significant, statistically significant in the use of untied, but very much so in the use of tied syncopation. That's really a big increase. So that means, indeed, the amount has increased, and that's also a bit in sync with the study by David Euron on general American popular music, that the syncopation increased over that time. Now, then we said, well, okay, now we studied only this one-to-one pattern, but of course, because that's supposed to be the most typical one, but how about taking, just investigating all syncopation patterns that occur? And for this, we would use the Longo-Tiggins and Lee model just to determine all the syncopation patterns and then find out what are the most frequent patterns in syncopated bars and what is it really the case that the one-to-one pattern occurs that often? And indeed, the one-to-one pattern is this darker one. So both in the tied and the untied version, they are pretty prominent. Trying to skip over So in all, both in the ragtime and it even becomes the untied version, again you see here, becomes in the modern era even on the second place of all syncopation patterns used. Okay, so we were interested in, how did those syncopation develop over time, but we are now also interested in, okay, in a way we have now just analyzed, these little snippets and counting them, but those little snippets, they contribute to a metric weight feature, and you can see a very strong influence. Like here is, for instance, a pattern, the analysis of a right hand, where there are no untied patterns and no tied patterns, and as you can see, that's a perfect 2/4 shape. The more we have of, for instance, here, this has a lot of tied patterns in the middle. You see very low metric weights in the middle of the bar. So in the next step, we would like to not only count what patterns there are, but take the influence on the metric weight into account, such that we at some step might use the metric weight profile as a possible feature of, distinguishing ragtime from other styles. So again, we started with a music that we think is totally obvious. It's not hard to distinguish what a ragtime is. We will listen to it, but if you have to tell it, it's a less trivial question. And what we are now in is that we want to compare ragtime versus jazz because they have very related patterns, styles, sorry. And if you remember, one of the arguments was that ragtime was heavily influenced by South American dances, and the same is said about jazz. And so we were interested in comparing clave patterns that clearly come from that style. How do we find clave patterns and syncopation patterns in ragtime and jazz? And on a data set, on a newly created data set of jazz songs, we found out that indeed we have way more clave patterns in the jazz than in the ragtime. So we hope at some point, to be able to take those patterns that we have found in a way of trying to be able to distinguish closely related styles. Okay, my last example, I'm almost done, very short. It's about harmonic patterns, which is of course a missing melody, metric, and harmonic, and that is work that we have done together with Cordify, a music e-learning service that allows you to take a YouTube file, and it will display to you, if you play guitar, the chord labels so that you can play along. I think, yes, I have that trouble. Just want to show you very quickly how that looks and sounds like. Okay, so.
Left here, it's coming and it won't be asking. Got nothing when there's nobody left in your home again. You gotta stop.
So you get the picture, yeah? Let's move that back. Now, Codify has each month 1.5 million users, and they listen to it 4,000 hours. And while they have an automatic chord recognition algorithm, which doesn't work perfectly, users are allowed to annotate chord labels. So that means they have now lots of annotated data. And we wanted, specifically since harmony is known to be ambiguous and that many places people could disagree, whether you play, for instance, a C major chord or a G major chord, we wanted to take the advantage of taking, these different annotated labels for studying whether by combining the different sources we could come up with a better way of chord labeling. And this was actually a paper at last year's Izmir, where we would use a data fusion model that starts here from different sources from the MyRix competition on chord recognition, and uses those as input to do data fusion for finding, in a way, the best possible chord recognition that consists of those 3 steps. You start with random probabilities, what chord could be where, and you take into consideration aspects of source accuracy, chord likelihood, and source dependence in a cycle. And in the end, you end up with something that looks like that. You see here the difference of each of the data fusion to the best performing algorithm in the Myrick's task. Here you see random, and here you see the majority vote. So the important thing was, do we get better than majority vote by taking data fusion into account, which also takes into account like what is the accuracy of a given source. And we could see that this is how much better we get than the best performing algorithm, and it's significantly also better than just the majority vote if you do it with data fusion. And so we hope to explore this idea of data fusion also now in other areas of music, because that's a very musical problem, right? That you have different perspectives on the same thing, different opinions. Perhaps you just don't take one, but you try to find a way of combining those different opinions and come up with more smart solutions than if you had just started with one. And just as a side remark, this is where we started, but in collaboration we also used this, in collaboration with Carnegie Mellon, we also used the data fusion for improving state assurance and machine state prediction from audio sources. So they have a lot of data on drones, like the audio that those 4 rotors produce. And we would take the data fusion model to take the information that you get from the 4 rotors to classify the audio signal and predict whether the drone is ascending or descending, and also use the same data fusion model, and it works pretty cool. So we started from harmony patterns and went into that area. Okay, last but not least. So I hope I showed a bit what I meant with what we can do with computation. We take a step back from assuming we are the expert and we know everything about the music, and trying to model some of that, and then hopefully come back with some insights on what we thought was perhaps true or perhaps was not that much true. And I think what we learned by that is, well, one of the beginning of digital humanities, the argument was, now we can do these things so fast, right? Fantastic. So that's the task of the high-speed idiot. But I also think we need to ask from the musicologists a little bit more patience with the time, with respect to how fast we can do the research, because still, we have to digitize the data, formulate the hypothesis, formalize it into a model, and then implement it, and then debug, and then debug, and then debug. And then we run the model, and then we do the statistics, and then we interpret the results, right? And I mean, all of this takes time. And I sometimes feel like, please also tell this to the musicologists who think, wow, now we have the data and we are so quick. Well, there is something to do before you get to that stage. And please have the patience with us. This is something we also had to tell the musicologists at the Mertens Institute, that we will not have the machine by tomorrow if they don't help us with their insights. But I also learned that, so we also need more patience, but what I definitely learned was that I feel like if I try to get a computer to answer a question to me, that I basically explain the music that I love to an alien who doesn't know anything about it. And if I am able to, explain that to the dumb computer, then probably that's a proof of check for myself. How much have I understood or perhaps misunderstood? So I think there's really a huge chance, besides all the nice applications that come with that, to learn something about the music that you're in love with, and to come back to, the chocolate cake. What we then get into is, layers of knowing. You thought you know this. Well, perhaps there was something true. You get deeper and deeper and deeper in this process of trying to understand what it is that you really know about the music. And I think there's a lot what computation really can do about trying to understand the music that we think we are expert of or we are beginners with. Okay, and just to give acknowledgements to all the people that have been involved with the research that I have just talked about, and I have a new PhD student, so I have finally also a female in the picture who just started, and she's busy now with taking the data fusion model for trying to take all those different pattern algorithms and see whether taking the collective wisdom we, can come up with smarter ways of finding automatic patterns. And thank you very much for your patience. Thank you.